In this video, I will explain about introduction for heat exchanger. Basically, this introduction will explain about how you do the analysis of heat exchanger. Okay, so analysis of heat exchanger, two different design tasks. So first one is in the question, specify the temperature change in the fluid stream and the mass flow rate. Okay, the required is to the designer needs to select a heat exchanger, and the second design task is in the question specify the heat exchanger type and size. For example, shell and tube heat exchanger, double pipe heat exchanger, or cross flow heat exchanger, and then fluid mass flow rate given in the question, and then the inlet temperatures. So required is the designer needs to predict the outlet temperature and heat transfer rate. Okay, and actually in the analysis of heat exchanger, we may deal with two types of method. The first one is log mean temperature difference. I believe that you already heard about the log mean temperature difference, because in the question there will be delta T log mean. And then another method, it is new, but previously already you already heard about it, NTU method, effective NTU method. So if we refer to both of these design tasks, okay, which of those methods are suitable for these two design tasks? Okay, the first one is log mean temperature difference. The best suite for the log mean temperature difference is the design task number 1, because all the temperatures has been given in the question. Temperature change, it means that TC out, cold fluid in and out temperature, and then hot fluid in and out temperature given in the question, and then the flow rate is also been given in the question. So that the first design task is best suited for LMTD method. And the next one is the effectiveness NTU method, and this method best suited to task number 2, where in the question specified to you or given to you the information about the heat exchanger type and size, fluid mass flow rate, and then inlet temperatures. Okay, the best suite, which means that it does not mean that you cannot use this first method into first design task. It means that this effectiveness NTU method best suited for the design task number 2. Okay, so the analysis of heat exchanger can be greatly simplified by making the following assumptions. So before we do some analysis, or before we do analysis on the heat exchanger, we must understand that there are few assumptions need to be made in order for you to do your analysis. For the first assumption, steady flow. So in this first assumption, we are assuming that the flow in and out is at steady flow, where there will be no accumulation inside the system. Okay, mass in is equal to mass out. Okay, in energy analysis, so we do have some accumulation terms in that energy conservation and of energy or conservation of mass or any other conservation principle will have that accumulation terms. So when we are assuming that that flow or the system is in steady flow, therefore we are assuming that there would be no accumulation in the system. Next is kinetic and potential energy changes are negligible, as we can refer to the fluid mechanics concept. So this kinetic and potential energy is more on the Bernoulli's equation principle. As you can remember, that in the Bernoulli's principle, we have three types of energy terms in order for us to apply the Bernoulli's, in order for us to solve Bernoulli's equation, Bernoulli's principle question. So in the Bernoulli's principle, in the Bernoulli's equation, we have three different types of energy. First is pressure energy, second is potential energy, and the last one is kinetic energy. So why does we need to assume that the kinetic and potential energy changes are negligible? Because if we do really consider these two terms of energy, we are actually consider that there would be a changes in the mass flow rate or the velocity in the system, and this actually might affect to the properties of the fluid inside the system. Okay, therefore we are assuming that kinetic and potential energy are negligible. Okay, the changes are negligible. The third one is the specific heat of the fluid is constant. Okay, specific heat is dependent on the temperature change. Okay, if there is a change in temperature or increase in temperature or decrease in temperature, it will affect effects to the specific heat value of that fluid. So therefore, we assume that the temperature is constant. The change of the specific, there will be no change in the specific heat. So we are assuming that specific heat is constant. Okay, so it means that that specific heat does not affect by the temperature change. Okay, that is the third assumption that you need to assume in order for you to do the analysis of heat exchanger. And the fourth one is the axial heat conduction along the tubes is negligible. So for analysis, we know that if we refer to this double pipe heat exchanger, so we are considering the rate of heat transfer from inside of this first tube to the outside, where the outside tube is the shell of the tube, a shell of the shell side of the heat exchanger. Therefore, this actually is in vertical movement of the heat transfer. So what does this mean is we are considering the conduction throughout the axial or throughout the tubes. So which means we are considering the axial. The axial is this, the movement of heat from here to here. So in the analysis of heat exchanger, we are not considering these kinds of analysis. We are only considering in the vertical movement of heat transfer, where we will consider the movement of heat from inside of the tube to the outside of the tube. This is double pipe heat exchanger. So inside is for example, the hot fluid is in the first tube, this small tube, and then it will transfer to the cold fluid, where the cold fluid is in the shell side. So this movement is in vertical. Therefore, we are assuming that there will be no axial heat conduction along the tube. Okay, so the movement is only in vertical motion. Next is the outer surface of the heat exchanger is perfectly insulated. If we are referring to this figure, or if we are referring to the double pipe heat exchanger, okay, for example, this is double pipe heat exchanger. If we are considering the transfer of heat from inside of this tube to outside of this tube, the Q will be constant. And whatever Q that being released from the hot fluid to the cold fluid is the same. Okay? And the outer surface of this wall, outer surface of the tubes, where the second tubes will be perfectly insulated, which means that there will be no Q released to the surrounding. So if you are flowing the fluid, hot fluid inside of the shell side, so this is shell and then this is tube. So if you are flowing a fluid inside the shell, therefore the heat transfer will be from the shell to the tube. And if you are not assuming that this outside of the outer surface of this tube is perfectly insulated, there will be a loss of heat from shell to the surrounding. Okay, and that will make your analysis a bit complicated, because we know that the Q that transfer from the hot fluid to the cold fluid is the same, where the Q is constant. And this is the last assumption that will be made in order for you to do analysis of heat exchanger. So the first law of thermodynamics requires that the rate of heat transfer from the hot fluid must be equal to the rate of heat transfer to the cold one. Okay, which means that whatever values, whatever amount of energy being transferred from the hot fluid will be transferred to the cold fluid. Okay, and it will not release to it will not reduce or release to the ambience or release to any to the other parts of instrument or whatever. So that fluid from the hot, the rate of heat transfer from the hot fluid will totally transferred to the cold fluid. So the equation, in order for you to determine what is the transfer rate to the cold fluid and transfer rate to the hot fluid, will be the equation will be Q dot. For the first one is cold fluid. Q dot is MC, M dot C, mass flow rate cold fluid, times with CPC. The C, small case c is for specific heat. Okay, specific heat capacity for cold fluid times with Tc out minus Tc in. Okay, equal to Cc. C, this capital letter C is for heat capacity. Okay, this is specific heat capacity, whereas Cc is heat capacity. Okay, so where Cc, capital letter C, is equal to M dot C times with CPC, which is equal to this. Okay, so Tc out is always greater than Tc in. Why? Because hot fluid will transfer energy to the cold fluid, therefore the exit temperature for the cold fluid will be greater than the cold fluid in temperature. Okay, whereas for the heat transfer, the transfer rate of to the hot fluid, for the hot fluid, so will be used Q dot equal to mass flow rate hot water or hot fluid times with specific heat capacity hot fluid times with TH in minus TH out. Wait, here is TC out minus TC in. Why does this arrangement is a little bit different with this? Because previously we know that we will calculate the change of temperature equal to T exit minus T inlet. Why does this arrangement is different with this? Okay, as you can see here, TH in is always greater than TH out. Therefore, this value Q dot will be in positive value. So this equation will shows you what is the amount of energy, what is the rate of energy being transferred to the cold fluid. If you want to rearrange this equation the same as this, okay, you can write down it like this: M dot Cp H MH Cph T H out minus TH in. If you are using this equation, you will get Q dot in negative value. Okay, this negative value is represent release of energy. Okay, release of energy. Okay, when you want to equate this amount of energy with the cold fluid, for example, you want to calculate what is this TC out for the cold fluid, please do not bring the negative value, because this negative value is represent release of energy. You just take out the positive value or the value from the Q dot and equate with the m dot Cp, m dot Cpc times Tc out minus Tc in. Okay. Two special types of heat exchanger commonly used in practice are condenser and boiler. So this we have another equation that can be used in order for you to determine what is the rate of heat transfer. So since condenser and boiler undergoes the phase change process, we may use this equation, Q dot equal to m dot HFG. So where this m dot represent mass flow rate for that fluid, either it is hot or cold fluid, and then HFG is enthalpy of vaporization, where the phase change occurs, enthalpy of vaporization from the liquid to vapor or vapor to liquid. It will have the same values. Okay, you may use this equation also in order for you to determine what is the Q dot. And sometimes this equation used to determine what is mass flow rate for maybe condensed liquid. What is the mass flow rate for the condensed liquid in the heat exchanger, for example? So you may use this equation. Okay, so this equation, previously we know that the cold fluid is by using this equation. Okay, this equation, you know that previously you learned about how to actually calculate the rate of heat transfer from the inside tube to the outside tube. So by using the R total, and then maybe you will use overall heat transfer coefficient in order for you to determine what is the Q dot. Q dot is a delta T over R total. So what is the difference between this equation? This equation is actually calculate the amount of energy being transferred from the hot fluid by considering the increase of energy or increase of temperature from the cold in to the cold out. So we have this temperature Tc in, and then we have temperature here Tc out. So specific heat capacity is the amount of energy being absorbed or released. How much energy can be absorbed by those fluids. So when it multiplied with the change of temperature, you will know that how much energy is being transferred to the cold fluid. Okay, so here we are only considering the increment of temperature from Tc in and Tc out. Therefore, you will understand how much energy is being transferred to the cold fluid. That's why we are using this equation. So this equation, if you want to calculate what is the temperature inside or T surface inside or T surface outside of the first tube, you may use and equate with this Q. Okay, Q dot. Okay, this Q dot is actually to understand how much energy is being absorbed by the fluid. Okay, so therefore you will use this equation. And for the hot fluid, here we have Tc out, Th in, and Th out. So you will understand how much energy is being released by the hot fluid to the cold fluid. Okay, that's why you are using this equation. And the amount of energy being transferred from the hot fluid to the cold fluid is the same. We know that the Q is constant. Okay, Q is constant. Therefore, Q dot is being released from the hot fluid will be transferred totally to Q dot cold fluid. Okay,